A stellar mass black hole. These are the most common type in the universe, forming when a massive star between roughly 8 and 20 times the size of our Sun exhausts its nuclear fuel and collapses inward under its own gravity. The resulting object is extraordinarily small. The event horizon of a 10 solar mass black hole spans only about 60 kilometers across, roughly the width of a mid-sized city. Because the black hole is so compact, the difference in gravitational pull between your head and your feet at any nearby distance is immense. This difference is called a tidal force, and for a stellar mass black hole, it becomes lethal thousands of kilometers before you ever reach the event horizon. Your body would be stretched vertically and compressed from the sides, a process physicists call spaghettification, over the course of seconds. There would be nothing resembling an intact human body by the time the event horizon was anywhere near. You would never make it inside. Survival time is effectively zero, and not because of anything that happens within the black hole, but because of what the gravitational gradient does to you long before arrival.
An intermediate mass black hole. For decades, physicists debated whether this category truly existed, too large to come from a single dying star, too small to be the colossal objects anchoring the centers of galaxies. They are estimated to contain between a few hundred and a few 100,000 solar masses, and they are thought to form through the gradual merging of stellar mass black holes inside dense star clusters over millions of years. A strong candidate was detected through gravitational wave observations in 2020. The reason this range matters for survival is that as mass increases, the event horizon grows proportionally, and as the event horizon grows, the tidal gradient across a human body at its surface becomes progressively gentler. At the lower end of the intermediate range, around 100 solar masses, tidal forces at the horizon are still severe enough to kill on approach or at the moment of crossing. At the higher end, around 50,000 solar masses, you might cross the event horizon largely intact. Once inside, however, there is a singularity waiting at the end of every available path. The maximum survival time inside a black hole of this size ranges from fractions of a second to perhaps a few seconds of experienced time depending on mass. Enough to register that you crossed, not enough to do anything with that information.
Sagittarius, a star. This is the black hole at the center of our own galaxy, roughly 26,000 light-years from Earth. Its mass is approximately 4 million times that of the Sun, and it has been studied for decades through the behavior of stars orbiting it at extraordinary speeds. In 2022, the Event Horizon Telescope collaboration released the first direct image. At 4 million solar masses, its event horizon spans roughly 12 million kilometers, about 8% of the distance from Earth to the Sun. The event horizon is enormous by any human reference point, and a direct consequence of that scale is that the tidal force across a human body at the moment of crossing would be essentially undetectable. You would pass through the boundary of Sagittarius A star without any physical sensation of doing so. No jolt, no pressure, no signal of any kind marking the transition. The maximum amount of time you could survive inside before the singularity becomes geometrically unavoidable, derived from the internal space-time structure of a black hole of this mass, is approximately 62 seconds, about a minute. You would have roughly 1 minute of existence inside the most well-known black hole in the galaxy, with no way to transmit anything to the outside and no possible direction of travel other than inward.
M87 star. In April 2019, the Event Horizon Telescope released the first image ever captured of a black hole's shadow. And the object in that image was M87 star, sitting at the center of the Messier 87 galaxy, 53 million light-years from Earth. It is 6.5 billion times the mass of the Sun. At that scale, its event horizon is wider than our entire solar system out to the orbit of Pluto. The tidal forces at its boundary are negligibly small by any human measure. You would fall through the event horizon of M87 star the way you might pass through a doorway. No resistance, no sensation, no moment of drama. The inside would initially look, in many respects, much like the outside. Light from the universe behind you would still be visible, bent and reshaped by the geometry, but present. The time available to you inside before the singularity becomes the only possible destination, calculated from the same space-time geometry, is approximately 27 hours, just over a full day. That is not a marginal survival window. It is a meaningful duration by any human standard, long enough to think clearly, to observe the distorted light environment surrounding you, and to have a complete experience of the interior before the inevitable end. TON 618. Few objects in the observable universe approach this scale. TON 618 is a quasar located approximately 10 billion light-years away, and the black hole at its center contains an estimated 66 billion solar masses, placing it among the most massive black holes ever measured. Its event horizon spans a diameter of roughly 130 billion kilometers, about 40 times the distance between the Sun and Neptune. The tidal gradient at this boundary is so gentle as to be essentially meaningless relative to human physiology. Crossing it would be indistinguishable from drifting through open space. The light environment inside, however, would be unlike anything in normal space, redirected and restructured by the geometry of the interior in ways that have no everyday equivalent. The time available before the singularity becomes inescapable scales with mass, and for TON 618 it reaches approximately 11 and a half days, nearly 2 weeks. That is long enough to sleep, to think through what happened, to observe an environment no outside observer will ever see. The singularity still terminates every possible path with complete certainty. But the interval itself is real, a genuine duration of life, rather than a rounding error in the calculations. A rotating black hole. This is the most physically realistic category in this entire list because virtually all black holes in nature are spinning. The massive stars that collapse to form them carry angular momentum, and that spin is conserved and frequently amplified through the collapse. The theoretical framework describing these objects is called the Kerr metric, developed by mathematician Roy Kerr in 1963. A rotating black hole has a region outside the event horizon called the ergosphere, a zone where space-time itself is dragged around with the spin so forcefully that nothing, not even light, can remain stationary relative to the wider universe. Entering the ergosphere is not the same as crossing the horizon. Objects entering the ergosphere can in principle be expelled with more energy than they brought in, extracting rotational energy from the black hole itself in what is called the Penrose process. The interior geometry of a Kerr black hole is also structurally different from a non-rotating one. The singularity is not a dimensionless point, but a one-dimensional ring, a loop of infinite density that, depending on the entry trajectory, might theoretically be avoided. Some mathematical solutions within the Kerr metric suggest it is possible to pass through the ring along the rotation axis without encountering the singularity directly, entering a region with different space-time properties. Whether this translates to any meaningful extension of survival is a question the mathematics raises, but does not cleanly answer. The interior of a rotating black hole remains one of the least resolved areas in theoretical physics. A micro black hole. No micro black hole has ever been detected or confirmed, but general relativity does not prohibit them, and conditions in the very early universe, fractions of a second after the Big Bang, may have been extreme enough to collapse small regions directly into black holes with masses far below anything a stellar collapse could produce. A micro black hole might contain the mass of a mountain compressed to a size far smaller than a single proton. What determines survival near one is not the event horizon, which would be so small as to be geometrically invisible at human scales, but the radiation it emits. Stephen Hawking's 1974 theoretical work described a quantum mechanical process by which black holes radiate energy from near their event horizons, and this radiation is inversely proportional to mass. The smaller the black hole, the hotter and more intense its emission. A sufficiently small micro-black hole would radiate lethal levels of high-energy particles at distances well beyond any point of physical contact. You would be killed by radiation before you came close enough to experience any gravitational effect. The object itself would then continue evaporating, ending in a final burst of energy as the remaining mass converted rapidly to radiation. There is no scenario in which you survive an encounter, and no scenario in which you enter the interior. The event horizon of a micro-black hole and the human body are simply not operating at compatible scales.
A primordial black hole. Unlike every other type in this list, a primordial black hole was not formed by any stellar or galactic process. These hypothetical objects are thought to have formed directly from density fluctuations in the first fractions of a second after the Big Bang in regions where matter was compressed tightly enough to collapse before stars or galaxies existed. They have never been confirmed, but they remain one of the most actively investigated candidates for dark matter and the subject of ongoing searches using gravitational lensing and other indirect methods. Their mass range is extraordinarily wide. Some primordial black holes, if they formed very early and very small, would have already evaporated entirely through Hawking radiation over the billions of years since their formation. Others, formed later or from larger fluctuations, could have masses ranging from asteroids to thousands of solar masses, and could theoretically still exist in the present universe. The survival scenario depends entirely on which part of that range you encounter. A very low-mass primordial black hole would irradiate you fatally at a distance and then vanish. One in the stellar mass range would spaghettify you well outside the event horizon, exactly as a stellar mass black hole formed from a dying star would. The origin story is unique. The physics at the boundary is the same. A charged black hole. In theory, a black hole can carry net electric charge. The mathematical description of this scenario is called the Reissner-Nordström metric, and it produces a geometry significantly different from a non-rotating uncharged black hole. In practice, most physicists consider a persistently charged black hole to be unstable in a natural environment. Any charge it acquired would rapidly attract particles of the opposite charge from surrounding space, neutralizing it quickly. But the theoretical case is worth examining because of what the equations predict inside. A sufficiently charged Reissner-Nordström black hole has not one but two event horizons, an outer boundary and an inner one called the Cauchy horizon. Crossing the outer horizon commits you to the interior as with any black hole. The inner horizon, however, represents a surface beyond which the standard equations of general relativity lose their predictive power, a point where the mathematical structure of the theory itself breaks down in a particular way. Some analyses within classical general relativity suggest that crossing the Cauchy horizon might open access to regions of space-time unreachable by any other path. Whether this means anything physical, whether it translates to any real extension of experienced time or a different kind of interior, is contested, and quantum effects near the inner horizon are generally thought to destroy the classical picture before it can be realized. What remains is a black hole whose interior structure, even on paper, is stranger than the simple Schwarzschild case.
A near-extremal Kerr black hole. Every rotating black hole is defined by two quantities, mass and spin. Spin is measured on a scale from 0 to 1, where 1 represents the absolute theoretical maximum, the point at which the event horizon would reduce to a surface with no area and the singularity would risk becoming visible from outside, violating a principle called cosmic censorship. A near-extremal Kerr black hole is one spinning as close to that limit as physically possible without reaching it. Observations of certain active galactic nuclei suggest that some supermassive black holes are spinning at rates very close to the theoretical ceiling. So this is not a purely academic scenario. The interior geometry at near maximum spin is substantially different from slower rotating cases. The region between the outer and inner horizons compresses significantly, and the space-time curvature structure shifts in ways that alter the trajectories available to anything inside.
Some theoretical analyses suggest that under specific and narrow entry conditions, particular angles relative to the spin axis, particular initial velocities, the proper time available to an infalling observer in a maximally spinning, sufficiently massive black hole could exceed what the equivalent mass in a non-rotating state would allow. The precise extent of this effect remains an open question in the physics of black hole interiors. What is understood is that among all the variables a black hole can possess, mass, charge, and spin, it is spin approaching its maximum that produces the most significant departure from the simplest case, and that a near extremal Kerr black hole of sufficient mass represents the environment where the interior experience and available survival window would differ most dramatically from anything else on this list. If you want to help choose the next video topic, join our Telegram. Links in the description. Otherwise, click right here to watch the most unsolved plane crashes in history. Next.